All right, let's get started. Welcome to lecture 15 in Aero584 on guidance and navigation. This is going to be a first of three-part lectures on Kalman filtering. We won't get to Kalman filtering in this one, but we'll set up everything that we need to derive the equations for the Kalman filter in the next lecture. Okay, let's get started. So in this lecture, I'll tell you what filtering is, and more broadly, I'll tell you what state estimation is. Filtering is a special case of state estimation, in my opinion. We will need to use a little bit of probability theory to derive the equations of the equations for the Kalman filter. So we'll go through a little bit of random vectors. I'll talk about what the expected values are. I'll also discuss what covariances are and what exactly we need in probability theory to derive the Kalman filter. And then I'll talk a little bit about the optimal state estimation. I'll focus on the optimal predictor today, and Kalman filter will come in the next lecture. So why are we interested in this topic? Because that's the title of this lecture. Oh, not the lecture, but the course. Navigation, as you might have seen in the first few lectures from Professor Bernstein, navigation means determining where you are. So we are interested in finding where the vehicle is, where our vehicle, be it spacecraft or an aeroplane, is, and where it is going. And these two things are captured by the position and velocity. So we would like to know what the position of the spacecraft or the aircraft is, and what the velocity of the aircraft or the spacecraft is. Now, we can measure the position and velocity using sensors like radars and GPS, but these are not necessarily always going to be reliable or available all the time. For most of the application, we actually know what the equations of motion are, using the Newton-Euler method or the Lagrange method. We know what the equations of motion are, and we can integrate these equations to get our states, which include the position and velocity. But again, those models might not be perfect. They might have errors. You might not know the inputs exactly, or many other things can happen. But since we have some measurements and we have some equations of motion, we can actually combine these two, and we can estimate the states using the combination of these two objects. And that's the process that is called state estimation. So in state estimation, we basically combine the equations of motion with the measurements to estimate the state X. Okay, so what is state estimation? Like I said, you have a system, and you apply an input U to the system. Oh, I have a pen this time, so this should work. Oh, not switching. Yeah, there we go. So this guy is the input. You apply the input to the system, and you have a physical system. The input is applied to the physical system, and it produces an output Y. This is the output. Yeah, so the input is going to drive the internal state of the system in some way, and you're going to measure Y, which is going to be some function of the internal state of the system. And we only measure U because we apply the input U, and we measure the output Y because we have sensors. And we may have certain description of the system given by these maps F and G, dynamics map F and the output map G. And the state estimation is simply the process of estimating the internal state X here of the system using the input U, the measured output Y, and the functions F and G. So let's look at a simple example of state estimation. Suppose you have this car, and you apply a force to it, through an engine or whatever, and this car is going to move in one dimension. So using the Newton's second law, you know that the this car is governed by a second integrator, which is shown here. X double dot is the acceleration, and this is equal to the, applied force divided by the mass. But this is the scaled input. This is U here is the input, and I should say measured input. And W here is possibly the noise. Okay, so we can write this equation into the state space form by defining, well, we don't have to define anything. We just note that the derivative of x is x dot. So this, when I take the derivative of x, I get x dot as the first component. And I just look at this matrix times this vector, which or matrix times the state. So I know that I need a 0 of the position and 1 of the velocity. So I get x dot equals x dot. Okay, that doesn't tell us anything. But the x double dot, this equation actually comes from here. So x double dot is going to be u times w. So that's how we construct these three matrices actually. Usually it's called the A matrix, the B matrix, and the disturbance D matrix. Anyways, we can write a state space equation for this system. Now to get the, actually I shouldn't call this x of t because x of t is the position. What I want to say is x of t and x dot of t, which is the full state. Now to get the full state, we can just integrate this equation here, shown by star. But to integrate this equation, so to integrate the right-hand side, you obviously need the input and the disturbance W. And also you actually need to know what the initial conditions are because, integration requires you to know the initial conditions. So that's one way of doing it. But if you don't know what the initial condition IC and the disturbance W is, then you cannot integrate to find x of t. Now, let's consider the case where the velocity of this car is measured. This is usually the case because we usually have a speedometer or something like that to measure, a radar or whatever sensor, which can measure the velocity of this car. So in that case, we could write this output equation. Y, here is the measured output. And since we are measuring the velocity, we get x dot. And we just assume that we have some noise in our sensor. So Y is given by this equation. Now, instead of, in place of using the information x naught and W, we can actually use this information Y and construct the state, the equations of motion plus these equations, the output can give us an estimate of our state x and x dot, which is the position, and this is the velocity. So by measuring just the velocity and using the equations of motion, it might be possible to construct the state x and x dot. Okay, so generally speaking, why do we want to use a state estimator? So like in the previous slide I showed you, we don't necessarily measure all the states. We maybe only measure a few of the states. So if your state is x1, x2, and x3, and you only measure the second state, in that case, you don't know what. So this will actually give you just the second state. You may want to know what these first and third state are. So you may want to use a state estimator to find what x1 and x3 are using the measurement of x2. And so that's kind of obvious, and that's in the name. But there's another reason, and this is a little bit subtle. So let's suppose you have a measurement of the state x2. It just so happens that a filter or a state estimator can actually improve your estimate or the accuracy of your measurements. And towards the end of the lecture, we'll see how a state estimator actually does that. And another reason is that because a state estimator is allowing you to merge the measurements with the equations of motion to get the states, you can actually assimilate, or I shouldn't say assimilate, you can use these measurements which are coming at different rates to update your states. So it's one of the application of state estimation is also in sensor fusion. Okay, let's get more precise about these things. Let's start with the exact precise system that we are going to be working with. So in the last lecture, I showed you how you can get a discrete time system from a continuous time system. And in this lecture, and pretty much in all of the Kalman filter lectures, we'll assume that we are always dealing with discrete time systems. Just makes it easy. Same formulation is true for continuous time system, but we'll just stick with the discrete time system. So let's consider this system. This is an LTI system. The state x is a LX dimensional vector. That's what we are trying to estimate. Okay, by the way, I'll use this color scheme. I'll try to use this color scheme mostly in the slides. When you see something in the red, it means that it is unknown, and that's what we want. If it is in green, then it is measured. And if it is in blue, it is something that we compute on a computer, or on a digital computer. Okay, anyways, back to this. So we have the state xk, which evolves according to this right-hand side of this equation. The second term has uk. uk is the input. It's an LU dimensional vector. WK is the process node. I can't say it. Process noise. Wow, I couldn't say noise. Process noise. And the output YK is given by this equation, where again x is, we don't know what it is, we are trying to estimate it, and this guy VK is called the measurement noise. Okay, you must have seen this equation many times. So anyways, the goal of the state estimator is to construct an estimate x hat k of the state xk that is best, or optimal. Optimal in some sense, and we'll discuss how to construct a cost function whose minimizer gives you the estimator, and minimization of something is what leads to the optimality of the estimator. Okay, so let's start with a very naive state estimator. Let's say you have this system. This is the general system that we are discussing. Okay, you know what? I'm going to draw this again. Okay, changing back. This is our system. This is the system to which we apply the input and we get the outputs from. And let's say this is our estimator. So estimator is basically just the copy of the dynamics of the system. So we use the same A and you use the same B. So since we know what the input is, because we applied it, we use it exactly as is. We know the system matrices A and B, so we use those. Now, xk is what we are trying to estimate. We don't know this. So, we just started somewhere. We start x hat 0 at just 0. Usually x hat 0 is just going to be 0. And then this system is going to be inside a computer. So you can implement this. Now you don't know what the noise is. Since you don't know the noises, we don't have any noise in this estimator. Anyways, next we can define the error ek equals x hat k minus xk. So this is in the computer, and get rid of this. And this is the physical state. Now you don't have this physical state. You have this guy. So actually you can't compute ek. But just for the sake of understanding how this works, let's imagine that you have ek. Now you can actually write what ek plus 1 is. Ek plus 1 is going to be x hat k plus 1 minus xk plus 1. And using these two equations, this one and this one, we can actually find out that ek plus 1 satisfies this equation that I'm about to get. Okay, so I'm going to write the first one here, minus buk minus t1 wk. Okay, so this gives me, so I can cancel out the buks. I can collect the a from the first and third term, so that gives me x hat k minus xk, which is just ek. Okay, so that's ek, and then I have d1wk. Okay, that's exactly what I have here, so I was right. Okay, so the error actually satisfies this equation. And we can also write the solution for ek. Ek is just given by this equation. So if we know what the initial error is and the noise at all steps is, we can actually write ek. And if this equation actually satisfies, no, this solution satisfies the error dynamics. It's not that difficult to check. But anyways, let's keep going. So now we have to consider this equation, and then we figure out how this error is, how this error behaves. So what do we want this error to do? We actually want this error to go to 0. That's what we want. Why do we want it? Because limit k in, okay, this should be a z equal to. Because if we have this case, then the limit xk hat minus xk is going to go to 0, which means our state estimate is going to converge to the physical state. Now, if this matrix A is unstable or marginally stable, so if it's unstable, its eigenvalues are, the norm of its eigenvalues, or one of the eigenvalues is going to be larger than 1, or it might have eigenvalues on the unit circle. In that case, the effect of E naught is not going to die out. So in that case, your state is actually never going to, your state estimate is not ever going to converge to the physical state. And in that case, this method actually doesn't work. On the other hand, if A is asymptotically stable, which means all the eigenvalues of A are inside the unit circle, then this method may work. Well, it'll work in the sense that the effect of E naught will decay, and the rate of that decay is going to depend on the eigenvalues of A. And so this component is going to go away. And this component is going to be, this is basically a linear combination of all the wi's all the way from I equals 0 to k. So if wi's are small, your error is going to be small. So let's look at a couple of examples. So let's say you had a very simple system. You had a simple integrator, xk plus 1 equals xk plus uk. Now in this case, a equals 1, b equals 1, and d1 also equals 1. So this is a very simple system. I construct an estimator for this system, shown here in blue. And using the error equation that we just derived in the last slide, we can write the error solution, error at the kth time step, as this expression. So now let's consider two cases. Let's suppose x naught was 1 and x hat, the state estimate at the initial time is 0. So we don't have any information about the physical state, so we just set it to 0. So this implies that E naught is equal to x hat minus x naught equals -1. Okay, so E naught is -1. And we consider two cases. So in first case, we assume that for all steps, Wk is equal to 1. So I'm just going to keep on. So this Wi is 1 for all steps. So in that case, Ek is going to be E naught minus k times Wi. Actually, not even Wi, because Wi is just 1. So E naught minus k. So you see that Ek is actually growing. It's growing in the negative direction as shown by this plot. So this is, oh, I didn't put the y labels. So this is showing Ek. That's a very bad E. Okay, it's showing Ek for 10 steps. And you see Ek, Wk is constant and Ek is going down. While Ek is growing in the negative direction means that your state estimate is getting further and further away from your true state. So this method actually doesn't work if the noise is constant. Okay, anyways, what about a more realistic noise? This is a Gaussian random variable, or well, Wk is Gaussian random variable, which means that its probability distribution is going to be a specific shape. I will get into the PDF of Gaussians in few slides, but let's just assume Wk is a random number, which means that so this is the negative direction, this is the positive direction. This is how the PDF of a random PDF of a Gaussian looks like. We take samples from this, so we are going to be equally on this side and equally on this side, which means that our noise is going to be concentrated mostly in these regions. Anyways, I'm definitely digressing here. We'll get into more details about the probability, these Gaussian concepts. But let's just assume that our Wk is a random number between -infinity and +infinity with a Gaussian distribution. And this is how it looks like. It's basically keeps going between a negative number and positive numbers randomly. Now, if this is Wk and we add up all these things, we actually get this blue trace shows our error. This is called the random walk. And there are a lot of properties of random walks that you can study, but we're not interested in random walks. What we are interested in is the fact that the error, for a small variance of the noise, you can get pretty large errors. And this random walk actually keeps diverging. As time goes on, this bound is going to get larger and larger and larger. So your state estimate is going to be worse and worse and worse. The whole point of this exercise was to show you that this type of estimator actually does not work because, I showed you just two simple cases where the estimator failed. So it's not really that useful. Okay, so what can we do to make the state estimator more useful? So let's try to construct a better one. So this was the original system. We have a true system to which we apply the input and we measure the output. And now I'm going to construct this estimator. Now this estimator actually has, like I showed you earlier, the first components of the estimator are the original dynamics of the plant, of the system, so A and B. Now we are also going to inject this term. Now, what is this? This is actually the output error. This term, y minus cx hat k, is called the output error. Output error. And why is it an error? So we have an output, we have a measured output, and since we know that the output matrix is C, we can construct a computed output. This is actually measured, so, and computed. Since we know C, and since we have x hat, we can construct this C x hat. So this is the output of the computed system, and this is the output of the physical system. And the difference between those two is called the output error. Now we can use that output error and sufficiently scale it up or down and add it to the states. And that may help us actually improve the accuracy of our state estimates. So this gain K is what scales up or down this output error, and we'll see how that happens. So again, as in the previous case, we are going to define the error EK as x hat k minus xk, and we are going to write down the error dynamics, which is going to be EK plus 1. It's going to be given by x hat k plus 1 minus xk plus 1. Well, we know what x hat k plus 1 is. It's coming from this equation. I'm going to write 2 here and 1 here. So you just do 2 minus 1, and what you end up with is this equation. So now we have these 3 terms in the aerodynamics. This is the contribution of the measurement noise, and this is the contribution of the process noise. Okay, but let's look at this term. So this is a term which is defining the growth rate of the error EK. Now, from linear system theory, we know that if AC is observable, if the pair AC is observable, then the eigenvalues of this matrix A minus KC can be placed arbitrarily, which means that even if A was unstable or marginally stable and AC is observable, in that case, you can actually place the eigenvalues of A minus KC anywhere you want. You can put them all to 0. And if you put all of them to 0, this guy just completely wipes out. But you're still going to be left with the measurement noise and the process noise. So you have to judiciously choose your gain K so that you minimize the effect of your state error, the measurement noise, and process noise. So let's look at how we can do that by the use of a simple example. So let's say you have a simple integrator like we used in the previous case. So this is a true system whose state we are trying to, well, I don't need to say true, it's just a system. Let me erase this. So this is a system to which we apply the input, we measure the output, and we are interested in knowing the state xk. This is our estimator. Again, in this case, A is 1, B is 1. Actually, everything is 1. C equals D1 equals D2 equals 1. So we can write the aerodynamics for this system, and it just ends up being this. So it's a very simple expression, and we clearly see the contribution of the gain K in choosing the weights of the error, the process noise, measurement noise, and the process noise. So let's look at some of these, some of the responses for some choices of the gain K. Okay, so this is the aerodynamics, and we are going to run some experiments now. So we are going to run this estimator for 100 steps. I'm going to set x naught, the true state of the system, as this, and I'm going to set the estimator state as this, which means the error is going to be this guy. Actually, it's going to be -1. It doesn't matter really. And then we are going to assume that both the process noise and the measurement noise are zero mean Gaussians, which means 0 means that they are centered at 0, and Gauss, this one means that their variance is 1. And what I'm going to do is I'm going to compute this term, this expression. I'm going to take all the errors from the step 0 to step 100. I'm going to square it, and I'm going to sum them. And I'm going to call that this entity J of K. So cost for a specific choice of gain k. So let's start with the naive case, which was you just set the gain k to 0. When you set gain k to 0, in that case, you recover the naive estimator that I showed you a few slides back. The error dynamics is given by this equation, and we get some performance. Our cost is 24 units. Okay, now what if we had a non-zero gain k? So in this case, I choose the gain k to be 0.5. I run exactly the same experiment. In this case, our error dynamics is going to be given by 0.5 this equation. And note that I'm not, we don't have the error ek in usual applications, but this is an example that I'm running on my computer, so I can access all these variables. Anyway, so when we set j to 0.5, we immediately see that the cost has actually gone down. I think it was 24 for the previous case. And if we set k to 0.5, we immediately get much better performance, which means our error has dropped down a lot. Okay, so can we do better? Not really. So I increased k to 1. Now the cost has gone back up again. It's 12 instead of 10. So this doesn't seem to be a better choice of the gain k. But we have to choose one value of k. So how can you do that? Well, one way is to just run with a bunch of values of k. So I run the same experiment multiple times, each time with a constant value of k. I go from 0, 0.1, 0.2, all the way to 2. And the reason I'm only choosing 0 and 2 is because if I choose this value, if I choose k to 0, this becomes 1 times ek. Any smaller value of k is going to give me an unstable aerodynamics. Similarly, if I choose k equals 2, this guy is going to become -1. And any larger value of k is going to again give me an unstable dynamics. So I only want to deal with stable dynamics. I don't want to deal with unstable dynamics. So for all these choices of gain k, we see that the error has this kind of a shape. And again, this shape is going to be different. No, generally the shape is going to be the same, but these jaggedy edges are going to be different every time you run this code, because the random number generator is going to give you different noises. The statistics of the noise are going to be the same, but specific values are going to change. So anyways, you kind of see that the gain, which gives you the smallest value, is smallest error value, or not error squared over the first 100 steps is about 0.6. So how can we actually find this optimal gain? We don't know yet. Well, we would need a little bit of probability theory to find that out. Okay, anyways, again, in this picture, I'm showing you the errors for two values of k, 0.5 and 0. Clearly, when you use some some gain or some output error injection, your error performance improves. So like I said, I have shown you that injecting the measurement into the estimator can improve the estimate accuracy, but we don't know as of now how much we have to inject. And like I said, we are going to use probability theory to optimize the gain k. Okay, let me take a small break. Okay, back again. So let's keep going. Okay, so you may have seen random vectors, you may not have seen random vectors. So this is going to be a very quick tutorial on random vectors and expected values and the covariances. Anyways, so a random vector is a function which goes from the sample space to the real number space. And the value of the random vector function is the value of the random vector associated with the event. Well, this is a very abstract definition of a random vector, but we don't have to worry about this definition at all. I'll tell you exactly what is required to derive the equations of Kalman filter. Um, Anyways, if you've seen it, great. If you have not seen it, don't worry about it that much. So the probability density function of a random vector is a non-negative function fx, which goes from n-dimensional real space to real numbers and satisfies this property. This you might have seen. What this is basically saying is that the probability that the value of your random vector is going to be inside a set is basically just the integral of the probability density function over that set. So for example, if you have the probability density function looks like this is what the probability density function looks like for a uniform random variable. And you were asking, what is the probability that my number is going to be between this number and this number? You're asking what is the probability that the value of your random variable is between these two numbers. So that's just the area. This is a horrible drawing, but you get the point. That's just this area. That's just the area under the probability density functions between those two limits. So this is all it is saying. So we have an object called the expected value of the random variable x, random vector x. And it is really like the mean of the random vector, but it's not just the mean, it's actually the weighted mean. And the way it is defined is that you multiply the PDF by x and you integrate over. So each value of the random variable is actually weighted by its probability, and you sort of take an average, and that gives you the expected value. Again, this is just a definition, not very useful. The most useful component for us is the fact that the expected value is a linear operator. It's E is a linear operator. And when I say it's a linear operator, I mean that if you apply E to an expression like this, AX plus B, just using the definition of the expected value, we can clearly see that expected value of AX plus B is equal to A times the expected value plus B. So this is a fact that we'll use a lot. We can also define the covariance of a random vector. Covariance is defined, again, as this expression. This is just a math definition. And okay, two things. First, what is covariance intuitively? The covariance is like the spread of a random vector. So let's say if you had a random vector which looked like this. Okay, this is a horrible drawing. Let me redraw this. This was a bad drawing. Again, maybe a simpler case. So let's say you had a PDF which looked like this. So in this case, because these points near zero have high probability density function value, you're more likely to see these values. And you're very likely to see values which are outside. So that's the meaning of PDF. But what about this type of PDF? Well, actually, this doesn't make sense because the area has to be 1. So let me draw this again. Let's say you had this type of PDF. So this is PDF 1, and this is PDF 2. So in this case, the spread of the random vector is going to be very large, which means if you take like bunch of, let's say 1 million samples from PDF2, they're going to be spread over a larger distance. If you take 1 million samples from PDF1, they are going to be much closer to each other. So we say that the covariance of this random vector is much larger than the covariance of this random vector. So that's the intuitive sense of what covariance is. But anyways, covariance is actually mathematically defined as the expected value of deviation from the mean times the deviation from the mean transpose. Again, using the integral, you can write it like this. But the most important fact about the covariance is that covariance is not a linear operator. In fact, what it does in this case is you get the A outside on the left-hand side and the right-hand side, and adding a bias actually doesn't do anything to the random vector. I mean, it shifts its mean, but it doesn't change its covariance. So if you multiply it by something, if you scale it up, the covariance gets sort of a squared effect on the scale variable. So you get A on the left, A on the right, and B doesn't do anything. So again, these two facts are the ones that we are going to be using a lot. Okay, next, cross covariance. Cross covariance is also very much like the covariance. It's defined mathematically by this expression. So if you have two random vectors, one was this and one was this, and you were drawing samples from both of these. Well, actually, this one doesn't make sense because they look independent. Well, they might not be independent. Anyways, let me not digress. So if you had two random vectors, x and y, you can look at the covariance, cross covariance between x and y using this expression. Expected value of x minus mean of x times y minus mean of y. So cross covariance of x and y intuitively is the relationship, not really a relationship, but how much can you predict the values of y if you knew the values of x? That's what cross covariance is catching. But again, this is not really, we don't really need any intuitive sense. All we need from cross covariance is that they satisfies this expression. And actually, the covariance is just a special case of cross covariance. So if you find the cross covariance of x with x itself, you just get the covariance of x. So that was the short course on probability stuff, and that's all we're going to need to construct optimal filters, optimal state estimators, and Kalman filter. So before we go into the Kalman filter, this optimal state estimation and Kalman filter, I just want to mention something about the Gaussian random vector, because these, we are going to assume that a lot of things are Gaussian random vectors. So a Gaussian random vector is a special random vector. Well, not a special, it's just a random vector whose probability distribution function is given by this expression. Here, sigma is it's an n by n positive definite matrix. Whoops. Oh, yeah. It's a positive definite matrix, which means that the determinant is always going to be greater than 0. And mu is the mean. So, and x is our random vector. X is going to be an n-dimensional vector. And the PDF is basically given by this expression. This is an exponential which dies on each side of mu. So if you go way too left on the mu, this will evaluate to 0. If you go way too much on the right side of mu, it's going to evaluate to 0 again. So in pictorially, it looks like this. So in this case, shows it for 2 dimensions. This is where the mean looks like it is. It's going to be somewhere here. And the PDF dies down on both sides. So this is what you also call the bell curve. So all the samples drawn from this PDF are going to be inside this region. Anyways, so mu is called the mean, and the covariance is sigma, which is positive definite. And when I write W is from this set, which is parameterized by mu, mean, and the covariance sigma, we say this means that I'm saying that W is a Gaussian random vector with mean mu and covariance sigma. Okay, that's all we need to know. Now we are going to use the dynamics of the system and certain assumptions that we make about the noise to optimize this guy in the estimator. So in the estimator, we usually know this, we know this, we know this, we know this. We can compute this because we computed this. The only thing missing is the gain K, and we are going to optimize somehow. I'm going to show you how we optimize it. Okay, before we go further into optimal state estimation, I want to make one little reformulation. What I want to do is I really want to merge this process noise and measurement noise into one single random vector. So this is our system. Actually, don't worry about the system. What I want to do is I want to create a new noise vector, which looks like WK and VK. So if I want D1 WK and nothing else in the state equation, I can write this matrix D1 0, and when it multiplies WK and VK, it actually gives me D1 WK. And similarly, on the output equation, I'm going to write this matrix, which is going to give me D2 WK. So D1 WK and D2 WK are replaced by this matrix times a big random vector, and this matrix by this random vector. So basically, if we redefine our Ds, D1 and D2, as D1 bar and D2 bar shown here, we can write this equation. Now, the reason I'm doing this is because it makes it easier for the equations. Certain few variables actually collapse down to more, well-known variable choices. You'll see this. It'll become clear. Now, this actually does not mean that the process noise is equal to measurement noise just because it says W bar K here and here. These two values are not equal. Well, because of two reasons. They might be actually coming from different sources, in which case a W bar K, they might just be different samples of drawn from the same PDF. But more importantly, they're actually being different components of this W bar K are being picked up in the process noise and the measurement noise. So the process noise is not going to be equal to measurement noise. If we have these, instead of these zeros, if we had something else, we might end up with a cross covariance term, which actually we will in one of the equations. But in most of the applications, we just assume that the process noise and the measurement noise are not correlated, or they don't affect each other. Okay, so let's start looking at the optimal state estimation. We have this true system. Again, I've said that so many times. We measure the input to the system. We measure the output of the system. We don't know the noise. Again, I dropped the bars because you know what I mean by D1 and D2. These are not the same noises, like I said. Anyways, so we have the state equation and the output equation. We assume that we know all the system matrices, the input matrix, the dynamics matrix A, input matrix B, output matrix C, the process noise matrix, and the measurement noise matrix. They're all known. The input U is known. We are going to assume that the we are going to assume that the noise random vector WK is a Gaussian. And not only it's Gaussian, it's a special Gaussian with zero mean, and the identity matrix for the variance, which means it looks the same in all directions. So, you know, the changing D1 and D2, as I showed you in the previous slide, allows us to assume a very simple statistical property of the noise WK. We are also going to assume that the expected value of the initial state is X bar. Oh, actually, I didn't convince you yet that the Xk is a random vector. Okay, hold on one second for this. Well, this property also depends on the same idea. But anyways, let's start with the observations. So in this equation, as you can see, that Wk is a random vector. So if Wk is random vector, of course, Xk plus 1 is going to be random vector. If Xk plus 1 is a random vector, actually X at each step is a random vector. And Wk also adds is also added in this equation to get the output. So Yk is also a random vector. So the point is that the state Xk and the output Yk both are random vectors. And we assume that the expected value of the initial state is X bar, and the initial state is not correlated with the noise. So the noise has no effect on X naught, or X naught has no effect on Wk. That's what this is saying. The other thing to know is that Wk only affects k plus 1. It doesn't affect the state at step k. So we are going to assume that the covariance of Xk and Wk is 0, which is a very realistic assumption. All right, so we have the system. I told you all about the assumptions that we made. The estimator that we are going to consider is going to be the similar one that we have seen so far. We copy the original dynamics. We have the output error. We multiply the output error by this gain k, and we are going to try to optimize this gain k. Now, I convinced you that x, which is the state, and the measurements y, both are random vectors. Now, since this estimator is also driven by yk, which is a random vector, x hat k is also going to be a random vector. Okay, so next we are going to define the state error as we did earlier. The state error is going to be x hat k, the computed state, or at the estimated state, minus the true state. And this is also going to be a random vector because both of these are random vectors. And we are going to define the covariance of, well, we're not going to define it, it's just what it is. We are going to define this matrix pk, which is the covariance of the random vector ek. So pk is the covariance of ek. This is the most important, oh, let me erase that. Whoops. Oh, this is annoying. Okay, this is the most important equation that you want to keep track of. Okay, so an optimal state estimator chooses the gain k such that the covariance of the state error, which is pk, is minimized. And more specifically, we choose this matrix kk, which minimizes the trace of pk plus 1. What is trace? Trace is just the trace is just the sum of all the diagonal values. So trace of A is 1 to n, A, I. So if you have a 2 by 2 matrix, you just add A11 and A22, and that's what you get. That's gives you the trace. Okay, so PK is the covariance of EK. And in our probability crash course, we saw that the covariance is actually given by this big expression, expected value of the error minus the mean error, error minus the mean error transpose. Now, this is a giant expression. We would like to simplify it. We would want it to be simplified. We would be very happy if that expected value is the expected value of EK is 0. So let's see how we can make sure that the expected value of EK is 0. So we saw that the state error satisfies this equation. This is we saw this earlier in the simple case that I showed you a few slides back, and you can also check this. It takes 2 minutes. Once you have this equation, the aerodynamics equation, we can take the expected value of this whole thing. Expected value of EK plus 1 is going to be the expected value of this first term, the second term. And since these matrices are constants, I can pull them out I'm only looking at the expected value of EK and expected value of WK. Oh, by the way, the expected value of WK, very fortunately, because of our judicious choice of the noise characteristic, is 0. So we completely get rid of this term. We are only left with these terms. So the expected value of EK plus 1 is this guy. And if EK is 0, if this guy is 0, then obviously this guy is also going to be equal to 0. Well, okay, let's look from the other direction. If I assume that the expected value, no, I'm not assuming anything. If we were to have a case that the expected value of the initial state error was 0, then because of this equation, this one, the expected value of E1, E2, and all the way to EK is going to be 0. Now, what is the expected value of E naught? That's just the expected value of x naught hat, no, expected value of x naught hat minus x naught. And since the expected value is a linear operator, I can separate them out. And Ex, we know that this is equal to x bar because that's what we assumed. To make the expected value of E naught 0, all I need to do is set these two i's to 0. So the point is that if the expected value of the initial state x naught hat is x bar, then the expected value of EK for all values of k is going to be 0. So this fact right here is going to allow us to simplify this expression. We are going to basically lose these two expected value terms. Okay, so with this perfect case, amazing coincidence, we end up with the covariance matrix, which looks like this. Now, if pk is equal to this, then pk plus 1 is just going to be given by this. You just replace k with k plus 1. And we actually know what these expressions of ek plus 1 are. We know the dynamics of ek. So we can put back the expression of ek plus 1 here. It's given by these guys. So this whole thing is ek plus 1. And we transpose the whole thing, put it here. And then we carry out all the multiplications. Now the expected value, the error and the noise are not correlated. They are independent because the noise is actually affecting ek plus 1, not ek. So the noise and the error are uncorrelated, which means that I didn't write it, but I should have. Anyways, the expected value of ek times wk is going to be 0 because, like I said, error and the noise at step k are not correlated or are independent of each other. Anyways, we drop any term which looks like this. Then we are left with only these two terms. We have, because of the linearity of the expected value operator, we have A minus KC, this guy, A minus KC transpose, and similarly on the noise term. And since E is linear, we can take these two matrices out, and we know the fact that the expected value of EK transpose is actually PK. We replace this guy, and we end up with this equation. And we can also expand this equation out like this by carrying out all the multiplication. The reason I want to do this expansion is because I want to replace D1 transpose by Q. So I get a D1 transpose, which I replace by Q. I get D2 transpose, which I replace by R, D2 transpose. And then I'm going to get this term S, which appears twice, once as D1 D2 transpose, and then D2 D1 transpose. So it's going to be S and S transpose. So what are these terms exactly? You remember in the, let me write it here. In the in our system, the noise was entering as D1 WK. This is the process noise, and the measurement noise was this measurement noise. So if the mean of WK is 0, expected value of WK is 0, the expected value of D1 WK and D2 WK is also 0. So both of these process noise and the measurement noise, both of these the expected value of these noises is 0. However, what is the covariance of process noise? Let me write it here. So covariance of process noise is actually going to be D1 times the covariance of WK, D1 transpose. And this is from a couple of facts that I showed you in the probability slides. And this guy is actually the identity because we chose WK to have the covariance of an entity. So this becomes D1 transpose. Similarly, covariance of the measurement noise is going to be D2 covariance WK D2 transpose. And this becomes D2 transpose because covariance of WK again is I. So these terms Q and R are convenient ways of writing the covariances of the process noise and the measurement noise. And that was the reason why we reformulated the equations to have those special D1 and D2. Anyways, so we get this large expression of pk plus 1. Now, what do we do with this? We are now going to collect all the k terms. So now you see no k, 1k, 1k, 2k's, 2k's, 1k, 1k, 0k. So this is a quadratic equation in k's. Pk plus 1 depends quadratically on k. So I'm going to collect k terms. First, k's with no zero. Sorry, first term with no k's. Second terms with 1k, so k times this guy, and k trans this times this guy times the k transpose, and then the quadratic term. Now this is a quadratic equation, and when I'm going to take the trace of pk plus 1, I'm going to have a quadratic cost function, and since I said that the covariances are positive definite, this is a positive definite quadratic cost function, which means it has a unique global minimizer. And when we minimize the trace of this expression with respect to the gain k, we end up, well, that minimizer first is going to satisfy this equation, equals 0. So we take the first derivative, we take the gradient of trace pk plus 1, which is given by this equation, and we set that to be equal to 0. So the necessary condition for minimum value is setting the gradient to 0. And by setting the gradient to 0, we are going to find our optimal gain. So the optimal gain is simply given by this equation. So I move it to the other side, I lose the minus, and then I multiply the inverse of this guy on the right-hand side, I get this inverse. So this requires that this big term should be invertible or should be non-singular. Yes, non-singular, which can be guaranteed by having R as positive definite. So if R is positive definite and PK is positive definite, so sum of two positive definite matrices is going to be positive definite. Yes, so sum of two, well, this can actually be 0 because you can, well, Well, yeah, if C is 0, then this becomes 0. So you need a non-zero R value to have the inverse. So yeah, R needs to be positive. And in the matrix case, R needs to be positive definite for this optimal gain to make sense. So that's all there is to the optimal state estimators. You have the estimator, which is the same structure that we saw earlier with the output injection, where the gain K at each step is given by this equation. And this KK doesn't depend on anything except the noise characteristics, R and S, PK, which is the state error covariance, and the system dynamics and the output map. There is no B in this equation. There is no K, time dependency. KK explicitly depends on the system dynamics, the noise, and the state error. And the state error covariance is propagated using this equation. And yep, that's all there it is to the optimal state estimators. You just implement these three equations and you are good to go. So this is an LX by LY matrix, and this is an LX by LX matrix. So you implement these two and you have your optimal state estimator. Okay, let's look at a simple example and try to see if there is anything worth noting in the optimal state estimators. So let's look at the same example that we've been looking at in this lecture. So this is the simple integrator again. A equals 1, B equals 1, C equals 1. I'm just going to write those. A equals B equals C equals 1. And now the D1 and D2 take this special shape because, what I want is the process noise and the measurement noise to be uncorrelated, which means I want S equals 0. So S equals D1, D2 transpose, I think. Yeah, and if you carry out this expression, you'll see that S equals 0. So that's why I have the special choice of D1 and D2 here. Anyways, this is my estimator. Once I have all these values set in my gain expression, gain ends up being this quantity here, and the state error covariance is propagated using this equation. Because of these simplifying assumptions, the equations I showed you in the previous slides, they simplify to these simple expressions. Now, let's look at this equation. Now, this is a quadratic, well, okay, it's not a quadratic yet, it's a dynamic system. Let's just assume that the PK was going to converge. If PK converges to something, then PK plus 1 is going to be equal to PK. And then I can replace this guy with PK. Okay. And then I'm going to get a quadratic quadratic equation. And I can solve that quadratic equation. I'm going to get a negative solution. I'm going to get a positive solution. I'm going to throw out the negative solution. I'm only going to look at the positive solution because only the positive solution signifies the state error covariance in this case. So that P infinity, which is the converged PK, in this particular case actually looks like this. So we can find out what is the state error covariance, what the state error covariance converges to in this case. So your state error covariance is going to be 1.62 in this particular case. And with the converged state error covariance P infinity, I can calculate what the optimal gain is going to converge to. And that K infinity is given by this expression, which evaluates to 0.62. And if you remember that plot that I showed you, I don't know, on the 10th slide, it looked like it had a minimum at 0.6. So we were actually pretty close with that one numerical study. Yeah, that's it. This is how we can construct optimal state estimators. But is that always, is that all, or no? That's not the question. The question is the optimal state estimator always improving the accuracy? So it's very easy to construct. Do you just construct it and implement it, or do you have to be careful about implementing it? And the answer, of course, since I'm asking, is yeah, you have to be careful. So let's look at what can go wrong. Now you have this state equation. No, the real system. You have measured input, measured output, and I'm going to construct these special matrices for for the measurement matrix and the process noise matrix and the measurement noise matrix. And the special thing here is that the C matrix is 1, which means I'm actually measuring the entire state. Well, the state is just a scalar. So we are measuring the state, but we have a noise corrupting that measurement. And the covariance of that measurement is given by R. And so this is equal to D2. And I showed you that R equals D2 transpose, or D2, yeah, and this evaluates to R. Okay, so our measurement noise is R. Similarly, our process noise is going to be Q. Big Q is going to be small q. And using all this data, we can construct an estimator. We replicate the original dynamics where the gain, optimal gain Kk is given by this expression, and the state error covariance is propagated using this expression. Okay, so we want to find out whether using an estimator is a smart choice. Are we always going to improve the accuracy of the state estimate X? We are measuring the state directly, but with some error. So can we just be happy with our measurement, or does this estimator really provide us any benefit? So let's look at the asymptotic behavior of this estimator to find that out. So let's assume that PK converges to P infinity. Actually, I haven't shown you that PK actually converges to P infinity, or PK even converges to anything. But, well, I haven't shown you, but it is true in the estimator's case. So let's just assume that PK converges, and whatever it converges to, we call it the P infinity. And when I replace, all the PKs and PK plus 1 with P infinity, I end up with this equation. Again, it's a quadratic, and we can use the quadratic formula to compute compute the analytical solution, compute the solution analytically for P infinity. And we are going to get one negative solution, one positive solution. We are going to throw the negative solution because PK by definition is positive definite. And that actually looks like this. P infinity is given by this big expression. Maybe we'll have this in the homework problem. You have to derive this from this quadratic to this. That'll be easy. Anyways, let's look at some special cases. So let's suppose Q was equal to 0. Q equals 0 means that your model is perfect. There is no process noise. So if Q was 0, this guy is 0, this guy is 0. This just evaluates to 1 minus a squared r, which means the whole thing goes away. P infinity ends up being 0. So P infinity, which is the state error covariance, is going to be 0, which means that your state estimate converges exactly to your true state, even if you have sensor error. If your measurements have error, but your model is perfect, no matter how bad your sensor is, the estimator state converges to the true state. This is pretty good. It's basically saying that if you're using the model, if you're using a very good model, no matter how bad your sensors are, you can buy a really cheap sensor, your estimates are absolutely going to be amazing, eventually, asymptotically. Okay, we can also see the effect of the process, measurement noise. So let's assume that the measurement noise is 0. In this case, if measurement noise R is 0, then this guy gives you 0, this guy gives you 0, and then you have a Q plus Q divided by 2, which means that the P infinity is Q, which means that even if you have a perfect sensor, which means R equals 0, the state estimate accuracy is bounded by the model uncertainty, which is saying that no matter how much you spend for your sensor, if you use the estimator, your state estimate is not going to be any better than what the model is predicting. Okay, so that means that you really should be investing a lot in having a good model, and you can get away with a cheaper sensor. So let's probe that equation a little bit more. So that equation, P infinity, let me show you that equation again. It depends on Q, A, and R. So what I'm going to do is I'm going to calculate P infinity for a bunch of different values of A's, for a bunch of different values of Q's. So let's just focus on this plot for now. So I'm going to evaluate that P infinity for various values of Q for a fixed value of R. So in each of the plots, the value of R is fixed. So in this case, R is 10 to the minus 6. And Q is given by this. And I do this for A equals 1. A smaller value of A and all the way to A equals 0. I don't have to consider the negative values because A only enters as a square. So even if I had a negative A, I'll still end up with a positive number here. So anyways, so all these traces correspond to different values of A. What is interesting here? So this is R. I'm also plotting the Q in black dashes. So Q is right here. It's basically X equals Y line. Now, what is interesting to see here? What is interesting is this. In this region, let me draw this region. Let me make the line here. In this region, this is the region where R is greater than Q. So this is R and this is Q. So Q is like 10 to the minus 10, R is 10 to the minus 6. So in this region, your P infinity, which is the state error covariance, actually is smaller than the sensor noise. So whatever your sensor noise was, your state estimates are actually much better than your raw measurements. But if Q was greater than R, which means that your model is worse than your sensor noise, in that case, your state estimates are actually much worse than your measurements. So this is the region in which you want to use a state estimator. If this is the case, you don't want to use the state estimator. So no state estimator. And this is yes, state estimator. So you want to use a state estimator only when the model process noise is much better or much smaller than your measurement noise. So you see the same trend everywhere, that when you have the process noise smaller than the measurement noise, your state estimates actually improve. So to answer the question, does the OSE optimal state estimators improve accuracy? Yes, they do, if the process noise is smaller than the measurement noise. Okay, before I end this lecture, I want to go through, I want to tell you one more thing. This is a little trick. This is really has nothing to do with estimators. This is just making the estimators work in a sort of an off nominal case. So let's assume that these noises, WK, because it's a vector, had bias in them. You remember I showed you bias means that there is a non-zero constant offset, which means that I can write WK as this expression. WK is a W bar. This is a constant. And this is the zero mean component of the noise. So, we mostly assume that it's a Gaussian. So this component is Gaussian. and this is constant, and that's what gives us the our noise. What if this was the case? So the optimal estimator actually doesn't work for this case. The optimal estimator only works when WK is a Gaussian. It doesn't work in any other case. I mean, it works in every case because it's in a computer, you can implement it. But the results that we showed you, that KK given by that specific expression is the optimal estimator, will not hold true. So what do we do in this case? Well, what we can do is assume that this unknown bias, W hat, is a component of the state. So I'm going to redefine a new state. I'm going to redefine this big XK as my original state. I'm going to augment this W bar here. And then I need the state equation. So big XK plus 1 is, I'm going to increment both the X's index and the W's index. X is simply given by this equation, which is just the true equation repeated here. And W bar, if W bar is W bar at step K, what is W bar at step K plus 1? Well, it's still W bar. So we can write the equivalent A, B's, and D1 matrices for this case when the noise has a bias. So with the original A, B, and D1 matrices, I'm going to get this AA. I can construct this AA, BA, and D1A matrix where WK tilde is a it's a zero mean noise, and we assume that's a Gaussian noise. Okay, so we dealt with the state equation. What about the output equation? Well, the same thing can be done with the output equation. I'm going to write D2WK as D2W bar plus D2W tilde, and that is going to be, now this is going to become the part of state, and this is the noise, and that's what will give me CA. So this is what you can do to deal with bias. And why is this important in this particular application or course? Because in navigation problem, we are going to be using gyro measurements. And gyro measurements, one of the biggest problems with gyro measurements is that there is a gyro bias. And if you integrate a gyro bias, you're going to get diverging errors, diverging state estimates, like I showed you in one of the slides in the beginning. So I think that is the last slide. Oh no, that's not the last slide. Yeah, I have to set up the story for filters. So today what we saw, the optimal state estimator, that state estimator is actually called a predictor. And there is another fellow. This is called a filter, and I haven't gone into filters yet. I will go into filters in the next lecture. So what is special with the predictor? Predictor actually takes the data up to step K. So it uses UK and YK, and it predicts the value at step, it predicts the value of the state at step K plus 1, X hat K plus 1. And as you saw that the estimator was X hat K plus 1 equals the dynamics plus KK times the Y, actually I should write it down. X hat K plus 1 was A X hat K plus BUK plus KK times YK minus CX hat K. So it is using UK and YK to construct X hat K plus 1. So this type of state estimator is actually a predictor because it's predicting a value into the future. And I showed you how to construct an optimal predictor today. In the next lecture, we'll talk about filters. Now, what are filters? Filters are using the input data and the output data at step K to construct an estimate of the state at step K. This is going to use a very similar idea of the estimator, but the notation is going to be a little different because of the community. There is a lot of not a disagreement, but there is a variety of notations people use, and that notation is slightly different than the predictors notation, and I will get into that notation. That notation has to do a little bit with probability, and I'll show you in the next lecture how we can construct a filter like state estimator, and how we can construct an optimal filter. An optimal filter is what is called as a Kalman filter. So Kalman filter is basically an optimal state estimator, which happens to be a filter. And that would be the end of the all the math. And in the next lecture, so in my fourth lecture, I will go through the application of these predictors and filters in the navigation problems. Okay, so to summarize, we can use measurements um, in the state estimators to improve the accuracy, to estimate the unmeasured state, and secondly, improve the accuracy of the measured state. And in the next lecture, I will derive the equations for the Kalman filter, and eventually we'll apply the Kalman filter to the navigation problem. Thank you so much. And again, if you have any questions, which I hope you have a lot of questions, not because I confused you, but because it's an interesting topic, you can send those questions to me at this email, and I will try to respond to you as quickly as I can. Thank you so much. Have a good day.